In this video, we're going to continue with the calculation of the moment of inertia. And in this example, we're going to look at the a uniform solid cylinder. So we want to calculate the moment of inertia of a uniform solid cylinder as shown in this picture right here. So we're told that it has a radius of r, a mass m, and a length of r. And we want to calculate its moment of inertia about the z-axis. So the way we do this is that we can write our dm. So the dm, so the mass that is in this shell, dm is given by rho times dv, which we can write as rho times l times 2 pi radius dr. And then if we calculate the I value, so this is just the integral of r squared dm, so this would be r squared, and then if you substitute the dm here and you do this integral, you end up with this value right here. So we know that the rho value is just the mass over the volume, and the volume is just the pi times the radius squared times l. So if you substitute this rho value here into this equation here, you obtain an I value of 1/2 m r squared. Now it says that what if the length of the cylinder in the figure is increased to 2L while the mass and the radius are held fixed? So the density becomes half as large. How does that change the moment of inertia of the cylinder? So in this case, the I value is not going to be affected. All right. Okay, now we're going to talk about the parallel axis theorem. So suppose that we've calculated the moment of inertia about the z-axis. How can I use that value to calculate the moment of inertia about a new axis that is parallel to the z-axis, and such that the distance between the two axes is r? So there is a whole bunch of mathematics that goes in here. I'm not going to derive all of these equations here, but so what we need to keep in mind is that, so suppose that we have two axes. One of them is the axis that go through the center of mass, and then one of them is the new axis, and I want to calculate my I value about this new axis. So there is a whole bunch of derivations that we can do here, but I'm not going to go into all of this. Instead, I'm going to write down the final result. So the final result tells me that the I value in the new axis is the I value about the center of mass plus the mass times the square of the distance, where the distance d is the distance between the two axes. So you can see that the d here is just the distance between these two the two axes. So we're going to do one application here. So in example number 10.9, we're going to apply the parallel axis theorem. So suppose that we want to calculate the moment of inertia about this new axis y prime, and we know what the moment of inertia about y is. Then we can use this equation right here. So the I value about the new axis is I value about the center of mass plus m times d squared. So d here is the distance between the two axes, which is L over 2. So again, we've already shown that the I value about the center of mass is 1 over 12 times ml squared. So if you substitute the d, which is L over 2 squared, and then you do everything, you get the I value about this new axis is 1/3 times m times l squared. So this is one application of the parallel axis theorem. All right. So now we're going to introduce one quantity that is called the rotational kinetic energy. So to derive that, so let's suppose that we have, so this is an object, and this object is rotating. So this object is rotating in the counterclockwise direction as shown in this figure. And let's say that the angular velocity is given by omega, then first of all, I can write down the kinetic energy for each of these individual masses, mi, as 1 over 2 times mi times vi squared. Then if you want to calculate the total kinetic energy of this system, so you want to sum over all the contributions that come from each of these individual masses, mi. So you can write this equation as 1/2 times mi times vi squared. But we know that vi is equals to ri times omega. So if you substitute vi is equals to ri times omega, so it means that this becomes ri squared times omega squared. And so if you look at this very well, you can write the rotational kinetic energy as 1/2 times all of this quantity here times omega squared, which we can also write as 1/2 times I times omega squared. So this is a rotational kinetic energy of a system that has a moment of inertia I and has an angular speed of omega. All right. So this is quick quiz number 10.6. Again, I'm not going to go over this. I'll let you guys take a look at that. So now we're going to compare. So very quickly here, we just want to show how to compare. So this is a very useful table number 10.3. It really tells you the relationship between the rotational motion and translational motion. So if you look at angular speed, so angular speed omega is just a change in the angle with respect to time. And then you have the translational speed v, which is dx by dt. Now angular acceleration is alpha, is the omega by dt. Translational acceleration is a, which is dv by dt. Now Newton's law can be written as sum of torque is equals to I times alpha, where I is the moment of inertia and alpha is the angular acceleration. So for translational motion, this is written as sum of forces equals to mass times acceleration. And then we know that if the angular acceleration is constant, I can write down these motion equations right here. Also, if the acceleration is equals to constant, I can write down all these equations right here. Then I can calculate the work done. So the work done is the integral of the torque times the theta. The work done here is the integral of force times dx. The rotational kinetic energy here is equals to 1/2 times the I value times omega squared. The kinetic energy here is 1/2 m times v. All right, so again, this is just to show you the relationship between the angular, so rotational motion and translational motion. So this is a table that you guys want to make sure that you understand how to use this table, because if you know how to solve problems in translational motion, then you can apply the same principles and concepts to solve problems in rotational motion. All right, now we're going to look at this example here. So we're going to apply conservation of rotational kinetic energy to solve this problem. So this is example number 10.11. So we're looking at a rotating rod. So we suppose that we have a rod that has a length of L and mass of m, and is free to rotate on a frictionless pin passing through one end. And then we're told that the rod is going to be released from rest in the horizontal position. What is its angular speed when the rod reaches its lowest position? So this is the rod at t equals to 0, so this is going to be released from rest, and then it's going to swing in the clockwise direction until it passes through this point right here. So we want to calculate what the angular speed when it reaches this lowest position right here. So again, I can do conservation of energy, so I could just say that the change in the kinetic energy plus the change in the potential energy is equals to 0. So again, I can say that the final potential kinetic energy is 1/2 I omega squared. The initial kinetic energy is 0 because it starts from rest. Now the final potential energy is 0, and the initial kinetic potential energy is just 1/2 times m times g times r. So again, so the final potential energy is 0 because at this point, the distance from So at this point right here, so if we pick this point as my reference point, then at t equals to 0, because my center of mass was here, then there's a height of L/2 that I can use to calculate the change in the potential energy. So it means that my potential energy is going to go from so the final value is 0, the initial value is just 1/2 times m times g times L. So again, if I solve this equation here, I can get my omega value is the square root of 3g over L. And then if you want to calculate the tangential speed, you can just say that the center of mass speed is equal to r times omega. So r here is just L/2 times omega. So if you substitute that, you get 1/2 times 3 times g over L square root. And then it says that the tangential speed of the lowest point on the rod when it's in the vertical position is just going to be twice. So again, I'll talk about this later on, but you're going to see that the speed at the lowest point is going to just be twice times the v center of mass. All right. So now we just want to talk very briefly about the rolling motion of a rigid object. So if you have an object that is rolling, so basically we can distinguish between translational motion and rotational motion. So the picture on the next slide really explains what is going on. So suppose that we have an object that is rolling. So it's moving from this position right here to this position right here. So if you look at this figure right here, you can notice that by the time that it rolls from this initial position to this final position, then the distance that it has traveled must be equal to this s, where s is just the arc length. So it means that the distance that it travels is just the arc length, and we know that arc length is just given by r times theta. So it means that I can calculate the velocity is called the center of mass velocity, is just the derivative of s with respect to time. So this is equal to r times d theta by dt, which is equal to r times omega. Then I can also calculate the center of mass acceleration, which is just the derivative of the center of mass speed over time, which we can write as r times d omega by dt, which is r times alpha, because we know that alpha is just d omega by dt. All right. So if you analyze the kinetic energy of a rolling object, so the first picture that you see here is an example of a pure rotation. So you can see that the velocity is always going to be tangential. So this is the tangential velocity, which is just r times omega. And the center of mass velocity is 0. And then if this is pure translation, you can see that for pure translation, this object is just sliding. So if this is sliding, it means that every point is moving at the same speed, and this is called the center of mass speed, VCM. Now, if you combine translation and rotation, you're going to notice that, so if you add everything up, so you're going to notice that the center of mass will be moving with V equals to, it's just going to be the center of mass velocity here, and then a point at the top is going to have a much more higher speed compared to a point that is at the bottom. So a point at the top here is going to have a speed that is equals to twice times the center of mass velocity. Meanwhile, a point that is at the bottom here will have a speed that is equals to 0. And so we can write the kinetic energy again as just 1/2 times the moment of inertia times omega square. Now the total kinetic energy of the system has two combinations here. So there is the kinetic energy that comes from the rotational motion and the kinetic energy that comes from the translational motion. So we can combine those two together and write the kinetic energy using this equation.